things that we are supposed to learn today. uh, skills and dimensioning. Okay, so start by discussing on scales. So the term scale basically means that uh, you see, in engineering, a lot of components are much larger than what would fit in our drawing sheet. Okay, and if we take that example, then we would want to draw those objects in something called reduced scale. So basically, if something spans over, let's say, several meters, okay, we can scale it down by let's say uh, a 1 in 10 or 1 in 20 scale we can use. Okay, and bring it down to the size of our drawing sheet. Okay, now this operation is known as scaling. Okay, now in your title block of each drawing sheet, you know that there is a space reserved for scale. And from today's class onwards, you are supposed to mention uh, what scale are you using uh, for for a given drawing. Okay, for example, if you look at the corner of this screen, do you see this 1:1 scale that is mentioned here?
Yes, sir.
Okay, so currently we are drawing in 1:1 scale, uh, but not quite. Okay, not quite. That also depends on how we plan on drawing. So now the popular scales or the generally used scales are usually multiples of 2 and 5. Okay, so that is decimal system going on there. So scaling factors typically represented like this. Scaling factors, typical scaling factors would be 1:1 to start with. Okay, and if we are talking about uh, reduced scale, that means we are drawing objects smaller than they appear physically, then we are supposed to use reduced scale. For example, if I mention a 1:2 scale, that would mean that 1 millimeter on paper is actually 2 millimeters in reality. Okay, if something has a span of let's say 100 millimeter in your drawing sheet, that would actually be 200 millimeters when the object is actually manufactured. Okay, so these are the reducing scales. So 1:2, 1:5. Okay, the next comes 1:10, and then you would see the pattern. The next scaling factor would be 1:20, and then 1:50, and so on. So you understand how it is progressing, right? Can you tell me what would be the next scale?
So 1:100.
1:100. Yes, correct. So if you progress in this way, then the next next term in this series is 1 is to 100. So these are the different scales that you can use for your for drawing in reduced scale. Okay, these are the scaling factors that you can use. So these are the reducing scales, and then you can use enlarging scales. Okay, so the enlarging scales also work in the similar fashion. Okay, so let's say you can draw in 2 is to 1 scale, 5 is to 1 scale, and let's say 10 is to 1 scale, 20 is to 1 scale, and so on. Okay, now let's say if I'm using the enlarging scale of 20 is to 1. Okay, and something uh, uh, an object in real life has a dimension of 500 micron. Okay, how much would that be on my drawing sheet if I'm using 20 is to 1 scale, and if a given dimension in reality is 500 microns? Okay, that's just half a millimeter. So how much would that be on my drawing sheet?
So 10,000 micron.
And that would be how much millimeter?
So
How many microns make a millimeter?
So
so micron means basically 10 to the power minus 6.
You should know that.
10 to the power minus
10
6
cube
millimeter.
microns.
So the point is that if you are drawing in a 20 to 1 scale, and if a dimension is supposed to be 500 micron, in your drawing sheet you actually draw a line which is of length 10 millimeters. Okay, does that make sense? কোনো confusion?
No, sir.
Okay. Okay, so the next thing that you discuss is called types of scales. Types of scales. And here the word scales means where you can measure certain dimension. Okay, it's a meter for some sort of dimension. Okay, that's what the scale means here. Okay, so a plane scale is something that you use on a regular basis. Okay, for for all sorts of engineering drawing. Okay, which has certain dimensions marked on its side. Okay, so that thing is your scale. Okay, so the point of having a scale, so earlier we were discussing scaling factors. Okay, and we know what do I mean by scaling, whether it is reduced scaling or in enlarging scaling. We know what that means. Okay, so we don't precisely draw a given dimension the way it should be in real life. We either reduce that, then we would be using a reduced scaling, and the reduced scaling would look like 1 is to 1, in 1 is to 2, 1 is to 10, etc. So the number that is in the left hand side of the ratio, okay, that represents what's on the paper. Okay, and the number that is on the right hand side is what is being manufactured. So an enlarging scale would be like 10 is to 1. So if you draw 10 millimeters on your piece of paper, the actual dimension in real life is 1 millimeter. Now those are enlarging and reducing scales. Okay, rather scaling factors. Now uh, now let's say if you are making a drawing, okay, and which incorporates several components, and several components are supposed to be of different dimensions. Okay, So now every time you are working with a given dimension, okay, the dimension could be let's say uh, um, 1 meter or 2 meter or something, and let's say you are using a reducing scale of, let's say, 1 is to 50. Okay, so 1 meter is represented by 2 centimeters. Now how much is 2 meters represented with? uh, that would be 4 centimeters. But then if I have to draw 50 centimeters, that would be represented by 1 centimeter. That's why the scale is 1 is to 50. Now, do you do all of these calculations in your mind while drawing, or do you prepare a scale? So you basically prepare a scale where you have marked all the, uh, mm, necessary dimensions, okay, according to the given scaling factor. এটা কি বোঝা যাচ্ছে কি বলতে চাইছি? So you basically take a line, okay, and make divisions on that line, and the divisions would represent certain dimensions. Okay, so that's the line is proportionally divided into certain dimensions. That's what is scale. এই পার্টটা কি বোঝা যাচ্ছে কি বলতে চাইছি?
Yes, sir.
Okay, so in that you have plane scale, then you have vernier scale, then you have diagonal scale, scale of chords, and this much would suffice. And actually we would be only doing examples on plane scale, diagonal scale, and scale of chords. Okay, so let's take an example of plane scale. We would mention the problem statement, and after that we would know how to solve that one. Actually, the problem statement would clarify that how we are supposed to work on a given problem. So here is a problem statement. Construct a scale. Can you see the font on the screen, or should I make it larger?
Sir, please make it larger.
Construct a scale of 1 is to 4. Now, right at this point, you should note that I'm talking about a reduction scale of 1 is to 4. And earlier I mentioned some of the scaling factors which doesn't include 1 is to 4. Okay. Now you need to remember that the ones that are specified in the left, those are generally accepted. That means everyone accepts those scaling factors. Okay. But here we are only solving a problem. Okay. There we can make our own choice of scale. So let's take a scale of 1 is to 4, and then what we should do is so to show centimeters, okay, and long enough to measure 5 decimeters. Okay, so is the problem statement clear?
No, sir. Can you please
Yeah,
explain?
elaborate. I'll elaborate. Okay, so you are supposed to construct a scale of 1 is to 4 ratio, which is a reducing scaling factor. Now, the smallest division on that scale should represent centimeters, and the largest division should be should measure long enough to measure 5 decimeters. Okay. Okay. So okay. So the smallest division on that scale should be 1 centimeter, and the scale should be large enough to span 5 decimeters. Okay. Now, if the scale is supposed to span 5 decimeters, and you are using a scale of 1 is to 4, okay, so basically you need to divide 5 decimeters is as in 50 centimeters. Okay, that is 500 millimeters. Okay, so in millimeters, the scale that you draw on your sheet of paper should be of how much length? কি বলছি বোঝা যাচ্ছে?
স্যার আরেকবার বলুন কি জানতে চাইছেন?
হ্যাঁ, see, if the scale, the length of the scale, the total span of the scale is supposed to be 5 decimeters, which is 50 centimeters. Okay, that is 500 millimeters. Then when you are drawing it in a 1 is to 4 scale on your piece of paper, what should be the dimension of the scale?
125 millimeter.
125 millimeter. Yes, correct. So let's take a side of length 125 millimeter. Okay, so this is your first assignment actually. Construct a scale of 1 is to 4, show centimeters and long enough to measure 5 decimeters. Okay, acha. So now what I'm doing, I'm constructing essentially a rectangle, okay, of let's say of 5 millimeter thickness. Okay, so I have gone 125 in the right. So now 5 millimeter, and then 125 in this side, and finally I'll join these two lines. Okay, now this whole length, okay, which may be of 125 millimeter, that is supposed to represent 5 decimeters. Okay, so what I'm going to do now is to divide this into 5 equal parts so that I have each decimeter. So the way we make any number of divisions is we basically draw a line, draw circular arcs. But here in AutoCAD, when I try to draw a circular arc, I essentially end up drawing a circle. So what I can do next is I can split that into, I can split that into, okay, there is no nearest snap, nearest, yeah, nearest snap, and parallel, okay, 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 then I would trim this portion, also trim this portion. Acha, also need to trim this portion. Okay, okay, so I have drawn one arc, and now I'll make a copy of those along the length. So basically, I'm drawing the arc from the first point of intersection, okay, having the same radius. That's what essentially I'm doing. So in that way, I'll draw 5 divisions, or five times I'll cut the straight line. And this is how you know you draw parallel lines. So, or you rather, sorry, how you divide any given line or into five equal segments is let's say by joining these two lines, okay, and then you are supposed to draw parallel lines. So what I'm doing next is I'm taking a line starting from here and parallel to this one. So I'm taking parallel to this line. Okay, and maybe I can similarly draw such parallel lines. Okay, now this set of parallel lines actually divided the original line segment, which were supposed to represent 5 decimeter, into 5 equal segments. Okay, now what you can basically do is you can So until what has just happened, you could be using your construction lines, which are essentially thin lines, and it doesn't even matter if they are not quite visible. Okay. Now the actual scale needs to be constructed in thick lines. So for that, what we would do is we would in AutoCAD terms, you are actually supposed to create a new layer. Okay. And we would make it a thick layer. And we would make line thickness visible. Do you see line thickness here?
No, sir.
Okay. Line weight, this one. Okay. So basically, I'm just constructing this rectangle. Okay. Now this is not how thick it should be. It should be actually a little bit smaller. Okay. So you understand that rest of the lines are only construction line, and that scale right there is a thick line, and you are also dividing that into 5 equal portions. Acha, by the way, I can also have the perpendicular snap on. So this is what I'm doing. I'm just dropping perpendiculars, and that way I would have divided the entire line into five five divisions. Okay, each of 1 decimeter supposedly. Okay, each division is supposed to represent 1 decimeter. Acha, just endpoint, endpoint, endpoint. Okay, so now each division is only 1 decimeter. Now I need to have the smallest dimension as 1 centimeter. So this is how we do it. So you see this. Acha, by the way, what we do now? We now label uh, the different vertices of the scale. So the point in the left, okay, and let's say we mark it with dimension of 1. We would call it as 0. 1 is too small. So let's say with 2, 2 looks correct. Okay, so 1, we would label this one as 1, this one as 2, this one as 3, this one as, acha, okay, 4. Okay, yeah, I made a mistake. So this, the first division is supposed to be 0 actually. So I need to move this from here to here. Okay, so the first division is regarded as 0 because to the left of 0 we would have the subdivisions. So To the right of 0, we have divisions in decimeter. So 0 to 1 is 1 decimeter, 1 to 2 is another 1 decimeter. But between 0 to whatever is in the left side, okay, that's where we are supposed to have centimeters, okay. And uh, and that is what we would number later, okay. So now let's say I want to divide this line right here. I should go back to the original layer. So this line segment right here into 10 parts, okay. And I'm breaking this circle into two nearest locations. Okay, what's happening? I want to break this circle so I get an arc. So let's see if I take this point and then I would again break this circle. But I still get the entire circle. Okay, so possibly it doesn't work with a circle. Acha, let's try to draw an arc. Start, center, end. Okay, so start, center. Acha. Start, center, and end. Okay, and then I would make 10 copies of this, rather 9 copies of this. এক, দুই, তিন, চার, পাঁচ, ছয়, সাত, আট, নয়, 10. Okay, and thereafter what you would do next is we would join these two lines, and like before we would be drawing parallel lines. So now 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, now you can trim those lines. Of course, when you are drawing it on a piece of paper, you don't have to do all of this. So basically what I did, I have divided that 1 decimeter span into 10 equal segments, and now I have centimeters. Okay, so now draw vertical lines from the endpoints. Okay, and then I'll simply copy this vertical line.
I
Yes,
think there are 11 divisions.
I have taken 11 divisions: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Yeah, so I have done a mistake. So what I should be doing instead is okay, 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 okay. One, two, three, four, five, 6, 7, 8, and 9. I believe this time it is okay. And then again, we'll get rid of. Okay. And then what we can do is now join this intersection point and drop perpendicular. Two, three, 4, 5, 6, 7, 8, 9, and 10. So now you have this scale which is showing centimeters as well as your decimeters. Okay. Now you need to number this centimeters as well, and this is how you do it. Let's say you number it as 5 and this one as 10. Okay. So that completes the construction of your scale. Okay. So do you think this one can be done?
Yes, sir.
Okay.
Yes,
So
sir.
and also notice that this also shows your uh, centimeter as well as 5 decimeter. It can measure up to 5 decimeter and it is in 1:4 scale. Okay. Okay. So this is your first assignment. Okay. And now we would construct a diagonal scale. Now those of you who have purchased a complete geometry box, okay, there you would find a diagonal scale right there. Okay. And here actually you would see you would construct something very similar to that one. Okay. And I'll just Acha, by the way, if I were to represent, let's say, uh, represent 3.7 decimeter on that same scale, how would I do that? So from 3 to 0, I have 3 decimeter, and then I can take 7 centimeters from 0 to 7 divisions to the left of 0. Okay, that way I can have, so basically up to this. Okay, so that way I can have 3.7 decimeter. but this one shows something very different. Okay, it doesn't show the actual dimensions, and when you actually measure the distance using an actual scale, there also you would not be getting the exact I mean, you will not be getting 3.7 decimeters. You would be getting something else. You would actually be getting one fourth of 3.7 decimeters. Okay, so for some reason that is turning out to be that is supposed to be 92.5, and for some reason I have done some mistake in drawing, so that's why I'm getting 92.4. So this one you should not write. Once you measure the dimension, okay, it would look like mm, 92 millimeters or something, 92.5 millimeters, but you are not supposed to write 92.5 millimeters. You are supposed to write 3.7. Okay. Okay, so this completes the drawing. And now we would try to construct a diagonal scale. So these are the specifications of the diagonal scale that we want to draw. So construct a diagonal scale with RF 1:4000, showing 500 meter and showing, not showing, but measuring 500 meters and showing 1 meter as a least count. So I hope the statement is clear. So you're supposed to construct a diagonal scale whose uh, whose total length should be 500 meter and the least count should be 1 meter. Okay, so so you would construct a rectangle, okay, which in the horizontal direction should be 500 divided by 4000. So if you divide 500 meter with 4000, how much millimeter is it?
Sir, 125 millimeter.
125 millimeter, right? Okay, no, it should not be this small. Acha. So in this direction, it should be 125. And let's say if I take, in this direction, it to be In this direction, I'm taking it to be mm, 20 millimeter. And again 125 in this side, and then close. Okay, then I'm supposed to divide. So just like the scale example, I'm supposed to divide this into 5 segments. Okay, that way each segment would be 100 meters, and I'm taking this arc and making copies of it. One, two, three, 4, and 5. And now I'll draw parallel lines. So I'm able to divide this segment into this line into 5 equal segments. So here I'm just copying in AutoCAD. In your case, you're supposed to draw parallel lines. So if you align your drafter with the first line, then you can draw parallel lines from all the intersection points. Okay, so as usual, uh, these are representing hundred meters. It should be how much scale? So this is like 400. This is 300. This is 200. This is 100. Okay. So now we can bring in our thick layer and draw a rectangle. And the vertical lines. Okay, now I need to divide this segment. Okay, now in order to have 1 meter, okay, if I divide one of the segments, so to the left of 0, okay, into 10 divisions, then I have 10 meters. But in my problem statement, I'm supposed to get 1 meter. So what I can do now, let's say I'm again dividing the segment in the left into 10 parts. 2, 3, 4, 5, 6, 7, 8, 9, and that's not uh, sufficient. So then you have your 10. Okay. Now again, I can join these lines, and then I can draw parallel lines. Okay. So now if I take my thick layer and draw vertical lines, then each division here would be would be 10 meters, because I'm dividing 100 meters into 10 segments. 2, 3, 4, 5, 6, 7, 8, 9. Okay. So each segment would be uh, 10 meters. Okay. So this is what we are not doing now. What you would do next is to divide this vertical line, this vertical side, into 10 portions. Okay. And make copies. 2, 3, 4, 5, 6, 7, 8, 9, and 10. And then draw parallel lines. Two, 3, 4, 5, 6, 7, 8, 9, and 10. Now, the vertical length is not of any specific dimension. Okay. But then we would draw shoes. Okay. We would draw horizontal parallel lines from the from the divisions of the vertical line. Okay. And let's say from if we now join these set of lines, now look at this slant line. Okay, so at the base it is making an intercept of 10 meters. At this vertex it is making an intercept of 0 meters. So when it is in the first horizontal line, that is this one, okay, it is making an intercept of 1 meter, 2 meter, 3 meter, 4 meter, 5 meter, etc. Okay, so any dimension between 400 meter to 1 meter, sorry, any dimension between 1 meter and 500 meter can be shown using this diagonal scale. And for that, what we would do, we would simply copy or draw lines parallel to this oblique line right here. Okay, okay. So does this make sense to you now?
No, sir, did not understand why you draw the horizontal lines.
Okay. See, you know that for a triangle, if you draw a line, okay, which is parallel to the base, it basically intersects the two other sides of the triangle, okay, at the same ratio. এই পার্টটা বুঝতে অসুবিধা নেই তো?
স্যার আরেকবার বলুন।
বলছি, এক সেকেন্ড। One second. Okay, so this completes the drawing of the diagonal scale. Acha. Uh, Now look at this. If you have a triangle, okay, so imagine this ninth line from the this line, okay, from the zero, okay, and this side right here, this side of the rectangle, and this line between this small line over here, okay. So this small line segment over here, okay, that is 10 millimeters. Can you see that?
Yes, sir.
Okay, acha. Now all these horizontal lines are parallel to one another, and they are parallel to this horizontal base right here. Okay. Now each of these horizontal lines are equal distance away. So they basically divide the line in this vertical line into 10 equal segments, and they are all parallel to uh, parallel to the base. Okay, so that means they also intersect this line, or they also divide this line into 10 equal segments, because they are parallel lines. They are lines parallel to the base. So they intersect the two other lines into equal proportion. Is that clear to everyone?
Yes, sir.
Yes, sir.
Okay. Not only
Yes, sir.
do they intersect the two lines in the same ratio, the portion of the parallel line captured between the two sides of the triangle, they also bear the same ratio. তার মানে যদি this this entire line segment to this okay, so if this entire line segment is divided into 10 parts, and this line also is divided into 10 parts, so all you can see that this horizontal parallel lines are also that are trapped between, so this portion, look at the smallest triangle right here. So this is the 1/10 of the vertical line, and this is 1/10 of the oblique line. Okay, so what is trapped between the two of the horizontal line right there, that is also 1/10 of the length of this 10-meter right here. So this line segment right here is 1 meter. এবার কি বোঝা গেল কি বলতে চাইছি?
Yes, sir. Yes, sir.
Yes,
সবাই বুঝতে পেরেছো এটা? আরেকবার বলবো?
Yes.
আচ্ছা, আরেকবার বলছি। একটা ট্রায়াঙ্গেলের বেসের সঙ্গে প্যারালাল একটা স্ট্রেট লাইন, not only does it divide the two sides in the same ratio, but the portion of the parallel line that is trapped in between also bear the same ratio with the base. ঠিক আছে? এবার দেখো, এই যে বেসটা, তাকে এই হরিজন্টাল লাইনগুলো, মানে এই ভার্টিক্যাল লাইনটাকে 10 ইকুয়াল সেগমেন্টসে ডিভাইড করে। ওকে, and these horizontal lines are all parallel to the base. So if I look at this line right here, that divides the vertical line into 1/10 of the segment. So this portion that is above this horizontal line is 1/10 of the vertical line, which basically means this oblique line is also divided into 1/10 by that horizontal line. Okay, now the portion of the horizontal line that is also trapped in between, okay, that is supposed to be 1/10 of the base as well. সেটাও মানা যাচ্ছে তো? This portion of this horizontal line trapped between the vertical line and this oblique line is also 1/10 of this base. এটা কি মানা যাচ্ছে?
Yes, sir.
Yes, sir.
Okay, so that means similarly, if you look at all the other horizontal lines and their portion that is trapped in between, okay, that also just proportionately increases. So this is like 1 meter, 2 meter, 3 meter, 4, 5, 6, 7, 8. Then this one is 10 meter. Okay, so let's say if I ask you to mark certain length over here. Okay, uh, let's say if I ask you to mark, show 374 meters. Okay, so the question is, how do you do that? So from right, if you come from 300, then you have 300 meters. Now you have to show 74 meters. So on this base, you can go by 7 divisions, that is 1, 2, 3, 4, 5, 6, 7. Okay, that would be 370 meters. And then you need to move along this line right here, which corresponds to 70, by 1, 2, 3, 4. Then this much would be 174. So all I'm trying to say here is so this is 70 meters. then 71, 72, 73, 74. This much is supposed to be 374 meter. Okay, so basically you have to measure just like the plane scale. You can measure 370. So from 300 to 0 it is 300, then 1 2 3 4 5 6 7, so that would be 70. To measure the another 4 meters, you'll have to move obliquely. You need to move upwards but using the oblique line. So you once you go 4 divisions upwards, so I believe not this one but this one. Is it so? 1, 2, 3, 4. No, the earlier one. Okay. So that would be your 374. এই পার্টটা বোঝা গেল তো ডায়াগোনাল স্কেলে?
Yes.
এটা
Yes,
করা
sir.
যাবে তো?
Yes, sir.
Yes, sir.
Yes, sir.
Okay. Next, you would look into the scale of chords. তাহলে এর জন্য আমরা কি করব? We would take a line এর মধ্যে যে কোনো একটা পয়েন্টে সেন্টার নিয়ে, এরকম ভাবে হবে না, এরকম ভাবে নিতে হবে। যে কোনো একটা পয়েন্টে সেন্টার নিয়ে আমি একটা আর্ক টানলাম। ওকে, নাও taking the same radius, how do I take the same radius? সেন্টার রেডিয়াসের তো কোনো জায়গা নেই। এনিওয়েজ, now taking the same radius, draw another arc. So if I join these three lines, I'm supposed to get 60 degrees. But let's say if I make this intercepts, uh, I'm supposed to get 90-degree angle. So basically construct a 90-degree angle, and then you would want to divide into three portions. Now that would mean that you need to divide this 90-degree angle into 30-degree, 60-degree, and 90-degree. Now you know how to get 60 degrees, so that one you have already got, and that is by drawing the circle. Drawing a circle with the same radius or circular arc with the same radius. So this much is 60 degrees. Okay. And similarly, if you copy this circle from this center point to this as the center point, then if you join these two lines, then you have the 30-degree angle. Okay. Now you would want to divide this 30-degree angle into even three more segments. Okay. So basically you want 10-degree segments in the circular arc, which is of 90-degree. So basically the purpose of scale of chords is to give you angular measurement. Okay. So if you want to draw an angle of given degree, okay, so the scale of chords will enable you to do that. Okay. Now how you can divide this circular arc portion, one thing that you can do is by trial and error method. Okay. So basically take certain radius. Okay. Try to make an arc out of it. Okay. So take certain radius and try to make an arc out of it. Okay. And then from this side also you can try to figure out, you can take the same arc. and then check that the radius that you took measures between the two intersections. Okay, and that way, after few trial and error, by reducing the radius and increasing the radius, you would be in a position to give an approximate representation of the trisection of this angle. Okay, you might have also learned about trisecting an angle. Okay, uh, mm, the methods of trisecting an angle other than 90-degree or 180-degree are not very accurate. Okay, so these are all approximate method. You can use any of those methods to divide the angle. Okay, the trial and error method can also work. Okay, now once you figure out how much how much is the length of the chord, so basically the radius that you get from the compass, that is essentially the length of this arc. Okay, sorry, length of this chord. Okay, which measures 10-degree. So once you figure that out, okay, you can use that for each segment. Okay, so you don't have to use trial and error for each segment. For one 30-degree segment, if you can figure out how much chord length corresponds to 10-degree angle, okay, then you can repeat the process. So in the end, um, angle. So in the end, you would have uh, 10-degree segments marked like this. So what you can do next is, now you can draw circles or circular arcs to measure the chord length. For example, for 10-degree, this much is the chord length. No, this much marks the, so this one is the chord length. I'm not talking about the length of the arc, but the chord that is there. So basically, I'm talking about the length of this line, which basically represents the radius of the circle. So that one being marked on the horizontal line. Okay, so I can say expand this horizontal line like this, and accordingly mark the the chord length for each angular section. So this is 10-degree. Next comes 20-degree, and at this point it might look like that the 10-degree segment and 20-degree segment just is changing linearly. Okay, but if you keep on doing this operation, so if you move on to 30, then 40, then 50, then 60, of course, passes through the center of the original circle. So 70, 80, and 90. So if you do that, now you would realize that the chord length, the change in the chord length is actually gradually decreasing. Okay, so the gap between 80 to 90-degree is not the same as 0 to 10-degree. It's because we are not measuring the arc length, that would have been uniform, but we are simply measuring the length of the chord. হ্যালো, হ্যাঁ আমি এখন ক্লাসে আছি। কি বলবে বলো? V1 V2 are basically the rate of change of H1 and H2. So basically আমার মনে হয় কোশ্চেনটাতে জিজ্ঞেস করা হয়েছে যে উইথ টাইম কিভাবে H1 আর H2 চেঞ্জ করছে সেইগুলো ডিফারেন্ট ডিফারেন্ট টাইম পয়েন্টস তোমাকে প্রিন্ট করতে বলা হয়েছে টার্মিনালে। ওকে, So this is what it would look like. So note how the different degrees uh, are not equally apart. So if I now label those, okay. So this is 0 degree. This is 10, 20, 30, 40, 50, 60, 70, 80, 90. Now let's say your job is to mark 53 degrees. Okay. So now let's say your job is to mark 53 degrees. Now so far, uh, if you are if you have done angular trisection, of course you have done some sort of approximation. So although you would see that 10 degree, 20 degree, 30 degree, these spans, okay, they are non-uniform, which each of this measurement has approximation associated with it, okay, for any form of angular trisection that you have done. But then uh, here we are going to incorporate another set of approximation, okay. So for example, if I am interested in finding out 53 degrees, what I'm going to do is I'm going to divide this 50 to 60 degree portion into equal 10 segments, like the way we have done before. So for example, we would take a line segment like this, okay, on which we would draw certain arcs, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then we would join these two lines, okay, and draw parallel lines, 2, 3, 4, 5, 6, 7, 8, 9, 10. So the idea is it might look like a protractor, but the scale of chords is not a protractor. So you'd basically be given this line right here. So do you see this line from 0 to 90? So that's the line that you would be given. Okay. And on that, each and every angle would be marked. So how do you draw a given angle? For example, if you are supposed to draw 53 degrees, this is how you do it. So take a line segment and then take the radius up to 60, because 60 degree uh, angle is what you get when you cut a given arc with its own radius, okay. So you draw the circle with radius from 0 to 60, and you basically take the measurement using a compass and draw this circle actually over here, okay. And Then, taking this point as the center, if you take the other point as the one point on the periphery, okay, so keeping the same radius, if you draw another circle, then you have this 60-degree angle. So then if you join these two, this is a 60-degree angle. But so if you do the angular measurement, so this angle is 60 degrees, as you can see. But if you take, let's say, a radius which is from 0 to, let's say, this is 50, then 51, 52, 53. Please remember that the gap between each angle keeps on changing. So it's not that the gap between 0 and 10 and 80 and 90 are not same. That change that is happening with respect to the gap between each degree, okay, that change is happening continuously. Just wait for one. Okay, so I hope you get the idea that that now that I have divided the span between the chord length corresponding to 50 and 60-degree angle into 10 equal segments. Now I can take three of those divisions, okay, and that could represent 53 degrees for me. But but the thing is that is also an approximation, okay, because as you can see that the gap between each two consecutive degrees is continuously changing. So not only is it that between 0 to 10 degrees and 10 to 20 degrees, and then between 20 to 30 degrees the gap is changing. It's not as if the gap is changing between only 60 to 70 degrees and 70 to 80 degrees. It is changing continuously, which basically means that 53 degrees is not just, you know, 30% the distance from 50 degrees as compared to the gap between 50 to 60 degrees. That is an approximation that we are making. এই পার্টটা কি বোঝা যাচ্ছে?
Yes, sir.
ওকে, সো নাও আমি এখানে অটোক্যাডে করছি, তাই আমাকে একটা এন্টায়ার সার্কেল কপি করতে হচ্ছে। তোমার ক্ষেত্রে যেটা হবে, ইউ উড বি টেকিং দ্য কর্ড লেংথ বিটুইন 0 to 53, okay, so your 53rd mark, so that is 3 marks after 50, that you take from 0, that measurement you take using the compass, and then you take, let's say I'm going to call, uh, this one as P, then this center right here as Q, and wherever that chord length corresponding to 53 degrees intersect with the arc passing through P, I'll name that as R. So that way, PQR is approximately 53 degrees. You are kind of trying to linearize an angular scale here. Okay, so now if I join these 3 points, P, Q, and R, that is supposed to represent 53 degrees approximately. Okay, so we can measure that angle. For manual drawing, you can use a protractor. In my side, I'm using AutoCAD dimensioning. You see, it says 53 degrees because it is approximately close to 53 degrees. If I go for more precision, it would probably give me like 52 point something 95 or something. Okay, but since the precision is set at 0, okay, uh, that's why it is showing. That's why it is showing to be 53 degrees. I forgot how to change the precision in angular dimensioning, but it seems in angular dimensioning it is only providing degree values and not the decimal points. Okay, so that's why you are getting 53 degrees. Okay, which is an approximation, of course. But do you understand the concept of scale of chords? Do all of you understand the concept of scale of chords?
Yes,
Sir,
sir.
sir,
Okay.
can you please repeat the process you did from the
Yes,
beginning?
yes, from the beginning. So I drew an angle of 90 degrees. Okay. Now, for a starter, you can also do that using either a set square or your protractor. You know, there are numerous ways you can draw a 90-degree angle, right?
Yes, sir.
Uh, but maybe just to do justification to the process, okay, you can only use a scale and a compass. Okay, that way you can first draw uh, a 60 degree, okay, then draw a 120 degree. You know how to draw 120 degree, right? So basically that is just another 60 degree. Then you bisect the span between 60 and 120 degree to draw 90 degrees, something you have done various times in your school level, right? So you know how to draw a 90 degree using scale and compass, right?
Yes, sir.
Okay, so once you have drawn the 90-degree angle, I need you to trisect that angle. Now, trisecting a 90-degree angle is quite easy. So you see, the moment you drew that 60-degree angle, which is basically intersecting the arc, okay, with the radius of the arc itself, okay, that way you get 60-degree angle. So the other portion of the angle is 90 degree minus 60 degrees, which is 30 degrees, which is one third of 90-degree angle. Okay, the uh, then from okay, then from this point, okay, you can use the same radius and make a cut. Okay, so basically from this point draw an arc with the radius of the circular arc, that is this one. Okay, So if you take this radius and make a cut, so you basically get a 30-degree angle. So this point corresponds to 30-degree angle, and this point of course corresponds to 60-degree angle. So you have divided into 30 degree, 60-degree, and 90-degree segments. Now the span between 30, any 30-degree span, let's say it is between 90-degree and 60-degree, or between 60-degree and 30-degree, or 30-degree and 0-degree, any of these spans you can trisect. And there are numerous ways that you might have learned how to trisect an angle. There are various ways actually. None of those are accurate. If it is an arbitrary angle, none of those methods are accurate. Okay, all are approximate methods. Now you can also go with a trial and error method. So basically you choose a radius, make an intersection over here. From this point also you make an intersection. Okay, and now the gap between two intersections, okay, gap between two intersections should match with the radius that you took to make the intersections. Okay, so you can make a trial and error to find out the arc length which represents 10 degrees. Okay, once you have figured that out, that is universal, so you can use that for the span between uh, mm, 60 to 90 degree, span between 60 to 30 degree, or in the span between 0 to 30 degree. Okay, so that is with the division of the arc. So the arc needs to be divided into 9 equal parts. Okay, now arc has been divided into 9 equal parts, but from this point which is marked with 0, okay, from this point, putting the center of your compass right here, pin of your compass right here, take the radius corresponding to the chord length. So I'm talking about chord length. So basically I'm talking about the length between this point which is marked 0 and any angle. So if you take this much of radius, that corresponds to the chord length corresponding to 20-degree angle. This is the chord length. The straight line right here is the chord length corresponding to 30-degree angle. So taking this much as a radius, make an intersection on the horizontal line. Okay, and keep on doing this till 90-degree, and you would realize the gap between 0 and 10 degree is not same as 80 to 90-degree, and the gap keeps on reducing, and actually it is reducing continuously. So in other ways, that the gap between 0 and 1 degree is not same as the gap between 1 and 2 degree. Gap between 10 and 11 degrees is not same as the gap between 20 and 21 degrees, and so on. Okay, but then you are going to do another set of approximation. So earlier you did an approximation by trisecting an angle, okay, which is not 90-degree or 180-degree. Okay, now you are willing to do another approximation. Okay, for example, now you are asked to draw an angle which is like 65 degrees. So all you have to do is uh, you know divide the span between 60 to 70 degrees into required number of segments. If it is 65 degrees, only two segments would suffice. Then but then you are taking the division uniformly. Okay, so you are uniformly dividing 60 and 70, but you realize that because the chord length is not linearly changing with the angle value, which it should not, of course, because mm, uh, you see the chord length between 0 and 90, 0 and 90, the chord length is supposed to be r root 2, and the chord length between 0 to 60 should be r. So as you realize that r and r root 2 is not exactly the ratio of 60 to 90 to 60, right? Because root 2 is 1.41421, etc., and 90 divided by 60 would be around 1.5. So it's not quite changing linearly. The chord length is not quite changing linearly. You do realize that this length is r root 2. Do you?
Yes, sir.
Yes, sir.
And if I take up to 60 degree, it is r. Do you realize that?
Yes, sir.
Okay.
Yes, sir. Yes.
So all I'm trying to say here is, let's say, from 60 to 90, the angle has become 1.5 times, but the chord length has only been 1.414 times. Okay, which basically means it is not changing linearly. The chord length is not changing linearly. But then we are making an approximation, assuming that for a small segment of angle, the chord length can be assumed to be changing linearly. That's the idea, right? Any nonlinear function in a small segment changes linearly. So that's the idea. So basically, you divide 60 to 70 angle into equal, uniformly you divide, and then take required number of divisions. Say, let's say if you divide 60 to 70 into 10 equal divisions, then you take 5 divisions after 60 and take that to be representative of 65 degrees. 65 degrees of chord length when measured from this point, which is marked 0. Okay. We followed a similar way to draw an angle of 53 degrees. So how do you draw any angle with the scale of chords? So you take the scale of chords and you don't look at any circular portion, anything other than this line here. This line should suffice. So first of all, take a line segment with the length 0 to 60, which is PQ. Okay. Then from Q, with the same radius, draw an arc. And on that arc, we would mark whatever is the required angle. Okay. Now, so PQ is a segment, and then this PR and the extended portion, this is the arc on which we would get our angle. But again, if we take the radius from 0 to 60, then we would get this point right here, and we would get a 60-degree angle. Okay. But but what we have done here is we have divided the span between 50 and 60 degree, the chord lengths corresponding to 50 and 60 degrees, into 10 equal segments, and you go for 3 divisions after the 50-degree angle. Okay. So the chord length corresponding to 50, we would go 3 divisions after that, and by taking that much radius, we would draw an arc with center at P. The center should be at P. So P is a point equivalent to 0 over here. So from point P, we would draw an arc uh, with a radius corresponding to the chord length, of 53 degrees, or at least the approximate chord length corresponding to 53 degrees. So once we had done that, let's say that point, the or the where the that arc intersects with the arc passing through P, let's say that point is R, then you would join Q, which is the center of the angle, with R, and we would also join P with Q, then the PQR is the desired angle. Is that clear to you?
Yes, sir.
Okay, so this is all the drawing that you are supposed to do, and then I would like to mention few things about dimensioning today, uh, or at least that's what I planned. But I'll just briefly go through things about dimensioning. For example, the linear dimensioning can be treated as two types. So this one is called uh, unidirectional dimensioning. Okay. What does that mean? I did a horizontal dimension, I did a vertical dimension. The dimension is put the dimension is put in the middle of the arrow. Okay. So the arrow with two arrowheads. Okay. So the dimension line in that arrow, the arrow that represents the dimension, we erase some portion of the arrow, and in between we put the value of the dimension. Okay. And if it is in millimeter, we don't actually write the unit. But what's what's so unidirectional about this unidirectional dimensioning is, whether it's a vertical dimensioning or a horizontal dimensioning, we are representing both of them in a horizontal fashion, as if the person who is looking at the drawing is looking at it from the so if you mark the four sides of the paper as the top and bottom, left and right, the person is looking at it from the bottom. Okay. So they are trying to read it like all horizontal. Okay. Do you understand what I'm trying to say here? This is what is meant by aligned dimensioning. Unidirectional dimensioning, where whether you are dimensioning a vertical line or a horizontal line or any oblique line, the dimension is always a horizontal. The text in the dimension is always horizontal, and it is by horizontal I mean it should be in such a configuration that the person looking at it from the below should be able to read it clearly. বোঝা যাচ্ছে এটা?
Yes, sir.
Yes, sir.
Okay. The other way of dimensioning, and I am not sure how to do that in AutoCAD, would be called align dimensioning, where and for that I would try to show that on Paint. Okay, so now imagine this rectangle I am trying to put a dimension to. So for the horizontal dimensioning, this is how the dimension line should be. Okay, and the dimension text. Okay, so let's say this much is 20 millimeter, so I would write 20 on top of this one. And for a vertical dimension, I would go about it like this. Of course, the arrowhead should be completely dark, and there is certain ratio that I mentioned for the arrowhead. So if this is your arrowhead, if this is 1, then this is 3. So if this is 1 millimeter, this length should be 3 millimeter. It should be that narrow, and it should be completely dark. Okay, acha. So for this one, we do not write if this one is like 15, so the 15 is not written like this. The 15 should be written like this. Okay. Now you'd ask, if I had put the dimension from this side, would I be like, no. Even if I had put the dimension on this side, the dimension should be in this fashion. Text should be in this fashion. So as if the person who is looking at the drawing is either drawing it from the right or looking at it from the bottom, not from the top, not from the left. It is either seen from the bottom or from the right. So the text would look in correct configuration if either looked at it from the bottom or from the right. Okay, so um, that's about the your aligned dimensioning. Why do we say aligned? If it is a vertical dimension, it's a horizontal dimension, the text is horizontal. If it is a vertical dimension, the text is vertical. That's what is meant by aligned dimensioning. And in unidirectional, let's say for this box, so this is how we would write it. Okay, acha. There are a few other things for which probably AutoCAD window would be better. Imagine there is something like this, and you are putting a dimension. So this is some view of an object. So you are dimensioning this one, as well as you are dimensioning this one. Now you could either represent the dimension like this, or you could represent the dimension, let's say, up to this, similar to this one. Okay, these two are allowed. What is not allowed is when a larger dimension is placed before a smaller dimension, which basically means that this dimension line is cut by this dimension line of the smaller dimension. Okay, so this is not allowed. Okay, so if it is a larger dimension, you should bring it more outwards. So this would be the correct dimension. Is that clear?
Yes, sir.
Yes, sir.
Okay. If I am dimensioning a circle, this is not the correct way. Okay, although it shows in the AutoCAD like this, but this is not the correct way. Let's see what happens if I go with radius. No, this is also not correct way. Okay, so imagine I'm dimensioning a circle. Okay, and I want to show the diameter. So this is the center. So this much represents the diameter. Okay, going from one point on the circumference through the center to the opposite point, and this much would contain the this would contain the arrowheads of the dimension line. Okay, the dimension line extends further, then becomes flat. On top of that, you put phi. This one has a diameter of 20 millimeters, phi 20 as the diameter. Similarly, if you encounter a circular arc, or maybe even a circle, this is how you would mark the center. R10. Okay. So is it clear?
Yes, sir.
Okay. I cannot think of anything as of now you would be requiring. Okay. So once we okay, a few other things may be there. For example, every time I'm using a freehand line, it basically means there is some portion that I'm not showing. So it's only a portion of the geometry that I'm showing. Let's say this is a protruded part and shown like this. It basically means this is not a cylindrical portion. This is actually a square segment. So if I'm trying to draw it in an isometric view, this is how it is supposed to be. Of course, everything is, if I look at it from the top, so the smaller this larger diameter would be a larger dimension would be there, but all I'm trying to say here is that this portion is actually a square. Okay, so when you dimension this geometry, so you should mention that this is square. Okay, and I'm not able to align my cursor over here, so you mentioned this is square, so sq, and let's say this is mm, 10 millimeter cross 10 millimeter, so you mentioned that thing. So when we would encounter different things, okay, we would mention why certain what certain dimensions mean. Okay, uh, for example, imagine you have a pipe joint. So this is where the pipe has been cut. So this is the section that you are drawing. Okay, but the pipe. So basically, this is what the pipe joint is. So there is a pipe, and there is a flange coming out of it. So basically, a flat cylindrical portion coming out of it, which basically has holes through which you would attach your uh, nut and bolt. Okay, so you basically have these circular holes. For the sake of simplicity, I'm just assuming there are four of those, and then you draw the center line through the center line on which the center of each of those holes lie, and then you put a dimension about so-called PCD or pitch circle diameter. So basically, this represents the diameter of the center line, which contains the center of each of the circular holes. Okay, so basically the idea is you have a pipe, and again I'm drawing the section view. You have a pipe, and when you are joining with another pipe, you make a flange, which is nothing but a thin cylindrical protrusion. So this is the direction of the pipe. So in 3D, it would probably look like this. Okay, so this is the flange, and then you would have another pipe segment with the flange, and then you join these two flanges, and then the pipe joint has been made. Okay, similar to that. So that's where this PCD comes in. So things like that you would only learn when you encounter such problems, and as of now I don't think a lot of things has to be learned about dimensioning, but do keep in mind few of the things. One is this aligned and the unidirectional version of dimensioning, how you should put dimension for uh, diameter and radius. Okay, and also the ratio of the width and length of the arrowhead. That should suffice for the moment. Okay. Okay.
Yes, sir.
Okay. So I hope you have understood what are the assignments for the day. So yeah, just prepare those, and in the next class onwards, probably we will be able to start projections, discussing on projections.
Sir, what was the full form of PCD?
Pitch circle diameter.
Okay, sir.